Right. So quantum dots can be used in many different applications. In electronics, in medicine, in energy sector, where you use quantum dots in solar cell as well. Okay, but obviously in quantum computation, because in quantum computation, quantum dots can be used as qubits. So, as I said, that in qubits, you have to make sure that the the electrons actually, for example, if you consider electrons, if you play with electrons, then let's say there can be quantum dots that will quantize electrons for sure, but you can also quantize the spin, because electron comes with spin, up spin, down spin, right? So you can say that spin, quantized quantum dot. So all you need is, for data processing, or for information processing, all you need is how you encode data in terms of some physical quantity, right? In classical computers, you encode data through charge. Like, for example, in a classical computing unit, a gate, for example, all you do is you're charging and discharging a capacitor. When a capacitor is charged, you say state is 1. When it is discharged, you say the state is 0, right? The same thing you do it in a flash drive, your flash drive. You actually store charge and you discharge. When you store charge, you write data. When you discharge, you discard data. However, in quantum gates or quantum qubits, states 0 and 1 both become probabilistic. So, in other words, there is some sort of inherent parallelism. So, as I was explaining, in classical computers, you have to really deal with each bit, individually, one at a time. But in quantum qubits, you can actually go in parallel. That is very important, because it follows superposition, and superposition is nothing but a state which is basically coming from, a combination of all those, 0 and 1. Therefore, inherently, quantum qubits are parallel. So when you do parallel processing, things become faster, obviously. So that's the fundamental difference between quantum computer and classical computer. Classical means one at a time. Quantum means you can do many at a time.
Which will greatly improve the speed and accuracy of some of these equations that classical computers typically struggle with. And one of my next questions was in regards to, we were talking about medicine and the application of that. One of the most famous medical problems is protein folding simulations and stuff like that. And so these computers have the capacity to potentially solve or approximate some of these solutions that are pretty unattainable with classical computers. And so I was wondering if you could talk a little bit about, for example, we talked about energy storage and some other medical applications, but when we talk about qubit research and quantum research, what are some of the major challenges in some of those fields? Why are we still stuck with classical computing when it has such a great potential for all of these revolutionary ideas?
This is the most important question, actually. Yes. So, when it comes to computation, the very first step is encoding. You have to really encode the information. That's the very first step. As I said, that in classical computer, you encode it in terms of charge. There is charge, state is 1. There is no charge, state is 0. In quantum computers, the state has to be well defined, very well defined. It is highly sensitive to environment. For example, electrons spin, it can be a state. Up spin, let's say 1, down spin 0, anything in between, you can rotate spin actually. So But spin is highly sensitive to fields, you know. So quantum computers, for example, qubits, right? We talked about qubits. So qubits can be built from different, using different strategies. Qubits can be from quantum dots, artificial atoms, as I said. Qubits can be constructed by using superconducting nanowires, can be constructed from ions, oscillating ions. You can actually control those oscillations through laser, okay? For superconducting wires, you can actually use microwave to control the direction of the current flow, clockwise, counterclockwise. Those are your states. Quantum dot, spin, right? You can control using electromagnetic field. But, there are many, many different challenges. For example, something called decoherence is very important in quantum systems. Decoherence means losing data leakage. What we say leakage, we call it decoherence in quantum systems. For example, electrons or the quantum states can interact with, environment, temperature fluctuations, field fluctuations, or even force, and can lose the quantum information. Highly sensitive. That is why the computers that you hear about, right? From certain companies, industries are proposing. You will see mostly they are operating at almost close to zero temperature, absolute zero temperature. They cannot provide room temperature operation. We're not there yet because of data leakage, because of information leakage. So therefore, encoding is a big challenge, and when we are designing our own quantum qubits, based on quantum dots, in our group, we are designing quantum dot-based qubits as well as single photon emitters, where we are designing, let's say, quantum dots so that it can generate coupled photons, entangled photons for quantum communication. So when we are designing these systems, we see that a very interesting challenge, very important challenge rather, comes from the fact that, in quantum dots you have many atoms, working together. Now, when you create a cluster of atoms, irregularities is very important. Let's say you are supposed to make, let's say, 10 quantum dots. You cannot, right now, the technology that we have, you cannot maintain uniformity across the board. So these 10 quantum dots won't have the same size, shape, and the energetics will depend on their size, shape. Even if you maintain overall, geometry, uniform, but atomistically, you cannot really make sure that the atoms are exactly, located in the same place, for all these 10 quantum dots. So there will always be atomistic irregularities, and which basically will translate to information leakage. So it is very hard to design these quantum systems that will exhibit uniformity, and will show coherence. So decoherence is a big challenge, in quantum research. Now there are efforts, to combat that. That is, you can actually design some error correction circuits. These are basically redundant, devices that are used to correct errors.
Speaking of some research combating the challenges that quantum device research faces,
Yes.
I was going to ask you if there was like a project or some news in quantum research that you're excited about or that you heard recently that
Okay.
you're thinking, oh, this could be
Yes.
going towards a breakthrough.
So I just came to know, like a month or so ago, that when I was visiting Purdue, actually, they were talking about that Microsoft is actually designing quantum systems based on something called Majorana fermions. So these systems will be more stable, will have less variations, less leakage when it comes to fluctuations due to environment. So that is something new that I learned, and I will see what happens in that direction. Apart from that, obviously there are efforts in other places, Intel is making its own, quantum computers. IBM also has, so different universities also have their own efforts, But I think, I'll be following this effort by Microsoft, this Majorana Fermion-based system.
You mentioned there are other collaborators and universities and stuff working on quantum research.
Yeah.
And I was wondering if you had any like colleagues in the School of Physics or any other research projects here at SIU that you are a part of or that you are like interested in learning more about.
Very good. Excellent question, actually. At SIU, the Department of Physics, now School of Physics, has got a couple of faculty members actually that have been doing research in quantum computation. Some in algorithm domain, some in hardware domain actually. There is an excellent effort actually from our physics department in the area of quantum correction, like error correction, and they are developing algorithms, along that line. I know there is someone who's doing photonics-based quantum computation, So these are all promising efforts. State of Illinois is also trying to lead this effort actually. That's what I came to know over this summer.